currently what we have in computers is the processing and memory are in different places. So in between you have the bus that you have to move the data back and forth. And this is the von Neumann bottleneck that limits the processing speed of our current computers. If you compare that to the human or biological brain, you know that there are the memory and the processing are fundamentally linked with the synapses and the neurons. And the whole idea of neuromorphic computing is to mimic the biological brain in chip. So you would have the membristors there as synapses, and then you would have neurons, and then you could have the processing and the memory in the same place. And then you don't need this fetching and storing of the data back and forth. So what we do is that we have this memristor, we're making these memristor arrays where you have the memristor here is in between in all these cross section places here. So you have top electrodes and bottom electrodes, and in between you have the memristor. And what we use is this material that is a manganite. It's calcium, gadolinium calcium manganese oxide with actually quite little gadolinium in it. And then we have an interface to aluminium. And the actual device is actually this interface between the GCMO and aluminium. So the physics happens here. And this is something that we have patented, and the material as a memristor, and we believe in this material for reasons I will come to. The changing of the resistance state is actually due to electrical control of the oxygen vacancies. This is very much similar to some other memristor materials, but unlike the most common ones, we don't rely on these filamentary paths. Instead, this is a scalable process that scales with the area of the device.
Yeah, capacity.
Titanium oxide or hafnium oxide or these sort of more usual oxides. A similar kind of area. How do I say? Area interface is seen in other manganites also, like praseodymium calcium oxide. And the idea is that when the oxygen moves, oxygen vacancies or the oxygen moves around, you will have high resistance state or low resistance state depending on how much the aluminium oxidizes or not. And but the difference between our material and, for instance, this praseodymium calcium manganite, that is there's quite a lot of research groups working on that, is that a GCMO in the calcium doping regions that we use is actually almost metallic. So the resistivity is quite low, which means that we can actually make this bottom electrode from the same material than the interface. So we don't need a very many layers in between. In addition, since the whole thing is based on defects, so oxygen vacancies, it's very defect tolerant. So you can use it in different extreme temperatures or radiation environments and stuff like that. Yeah, this is the first things that we did was on single crystal strontium titanite. We are working on putting it on silicon. This, but we can do it on lanthanum aluminum oxide, which currently allows us to make 2-inch wafers. And the way we do, because we don't have a very large, the pulse laser deposition system we have in-house only allows for very small samples, so we can't do a pulse laser deposition on 4-inch wafers or something like that. But that's not a real problem, because what we have done is that we can do this chemical solution deposition method of the film, so of the GCMO film. So since we can use the GCMO as the bottom electrode, we don't need to have any layers underneath it. So we can just do CSD on top of the wafer, calcine it, anneal it, pattern it, and then dice it. And afterwards, we can then put on patterns put on the other layers, aluminium layers and such like that. This is now on lanthanum aluminium oxide, and we have also done it on silicon with which has a small, very thin layer of strontium titanate on top. That has been a 4-inch wafer. The thing about this chemical process is that it's also doesn't contain any environmentally unfriendly chemicals, so it's safe, and we can do it in very low scale, in very low costs. So there's some figures of the progress of what we've done in the past years. So obviously we started at very crude things, and this is where we are now. We can do with the laser writer system we have in-house, we can do around 5 micrometer times 5 micrometer interfaces or devices at the moment. It's mostly limited by the equipment we have. And we have moved from this original solution where we have this lateral contacts between the aluminium and the gold to this capacitive version where we have added this layer of aluminium oxide in order to be able to control the size of the device in our system here in the crossbar. We have also done some modeling of the single devices so that we could actually look into and see whether they can be used in actual circuitry, so adding all the other things in the SPICE model. This has been published earlier. So, yeah, sorry. And this is now some fairly recent results on a set of crossbars that we've measured. So this is the structure I described, but this is in order to see the statistics. So basically we have about 90% yield at the moment. The endurance switching, so endurance is the one where you switch back and forth and see whether what happens, is fairly good. There's a 10 to 5 cycles here, and you can see that okay, there's some glitches here. It recovers, and you get quite nice division between the low resistance state and the high resistance state. And you can see that this is 1.5 orders of magnitude is the switching ratio here. Retention is the thing that you measure it over time and see whether it keeps its state. And depending on the pulse, you can do different cells. So usually we use the 2 millisecond pulse in between to switch it to a certain state and then follow it. We've tested also 20 microsecond pulse. You can still switch it. And the device we have for measuring these does not actually allow us to go much shorter pulses at the moment. There is some variation in the resistance states, but if you're aiming to the neuromorphic crossbar applications, that doesn't actually matter so much because, and what we are aiming at is this real STDP kind of a learning process, and this is what we want to test. And for that, we want to have this analog control of the devices. And here is an example. of some devices. So this is the statistical version, and these are just examples. So using different voltage ranges and different asymmetry, we can actually set the system into almost any resistance state we want in between the high resistance and low resistance states. And the ratio between the high resistance state and low resistance state is about 30 here. So this is the way we have shown that we actually do have the analog control of the system. This paper is currently just been accepted. It's probably not published yet, but it has been accepted. But we can send you the link if it exists. I'm not quite sure. About the IP, so we have the IP on this material, using this material on 4 memristors. We were the first group to actually do the full phase diagram. So it started from the very beginning of actually synthesizing the material. Nobody else had done that before. And then we have these two other patent families on the chemical solution deposition, and then on the manufacturing method of having only these 3 layers in between. Or only these 3 layers, the GCMO, aluminium oxide, and the aluminium as the whole crossbar network.
Maybe a few words, Paturi, now regarding the competitors. I guess the layers, you can do it with 3 layers, and the existing stuff, it's up to 70 layers, isn't it?
Yeah, it depends on who's doing it. Yeah, but
yeah, right,
generally
right.
There's a really a lot of layers, because all this hafnium oxide, titanium oxide, and these are really good insulators. So you need to have a lot of metallic layers as the bottom electrode, but we can use the same material as the bottom electrode.